Consider a person standing 12 feet from a light pole. The individual notices that the light casts a shadow of his body that is 5 feet long. If the individual is 5 feet 6 inches tall, how tall is the light pole? Create a diagram and label the unknown quantities. So, need a light pole. Here's my light. The person is standing 12 feet from the light pole, so I'm going to say this distance here is 12 feet. And here's this person. The individual notices that the light casts a shadow of his body that is 5 feet long. So over here we have a shadow 5 feet. And how tall? Oh, this is okay. The individual is 5 feet 6 inches tall, so this distance is 5 feet 6 inches. How tall is the light pole? So it looks like the light comes down and it's shining this direction, but it makes the shadow, and really that shadow needs to be about this long, 5 feet. Okay, that is not a very good diagram. I'll be doing better without this computer drawing apparatus. Determine the height of the pole and justify your position. So here's the height. Okay, let's see, this is what I notice. Right now I notice tangent of theta should equal the height over 17. Now, I think that's accurate. Let's see. The problem is there are two unknowns, theta and h, so that's not going to help me at all. Okay, what else? I do know this little triangle. I know that tangent of theta will equal 5 foot 6 inches. That's 5.5 feet divided by 5 feet. And look, since these are both equal, that means I can say h over 17 equals 5.5 over 5. Then I can find h to equal 5.5 over 5 times 17. And I get 18.7 feet high. And I think there's lots of other ways that we could solve this problem, but that's just the way that I solved it. Oh, determine an alternative method to find the height of the light pole. If you used inverse trigonometric functions to solve part B, use similar triangles to determine the unknown height. If you used similar triangles, use inverse trigonometric functions. So essentially, we used similar triangles because these two triangles, the little one and the bigger one, they both have 90-degree angles. They both share the angle theta. They're similar. We can set up this ratio of the height over the long piece equals the other height over the base and solve that proportion. So we're going to use inverse trig. And to use inverse trig, let's see, note we can just use the fact that tangent of theta is 5.5 over 5. Then we can use the inverse to find theta. Now when we do that, we get about 0.83 radii, or radians. Now we can go back to this equation that we had used earlier, because now we know what h is. Wait a second. We know what theta is. Theta is 0.830, and that equals h over 17, and that means that h equals 17 times tangent of 0.8330, which is 18.7 feet. Alright. A plane leaves a local Air Force base and travels due east. A radar station 45 miles south of the base tracks the plane and determines that the angle formed by the base, the radar station, and the plane is initially changing by 1.6 degrees per minute. Sketch a diagram of the situation and label the known and unknown quantities. So here's my picture, northeast, southwest. Here's the Air Force base. Here's the radar station, and then the plane sort of leaves the Air Force base and travels due east. Now, it says that the angle formed by the base, the radar station, and the plane is initially changing by 1.6 degrees per minute. So this angle, let's call it theta, is changing, and changing by 1.6 degrees per minute. So the change in theta with respect to time is 1.6 degrees per every minute. So what are the unknown quantities? This distance between the, let's see, between the plane and the, whatever this is, the radar station, that's an unknown quantity. This distance here between the plane and the base, there's another unknown quantity. And of course theta, we know its rate which it's changing, but it's a varying quantity. Define a function that relates the plane's distance from the radar station D, measured in miles, as a function of the elapsed time t, measured in minutes since leaving the base. So let's call our function f. Plane's distance from the radar station, that's what I had called r, but they called it d. So what I notice here from the Pythagorean theorem is d squared plus, actually equals, since that's our hypotenuse, it equals x squared plus 45 squared. That means that d equals the square root of x squared plus 45 squared. But we want our function to relate the plane's distance from the radar station D as a function of the time. So my function is kind of incomplete. Is there a way I could, like, I don't want to just have the function with x inside of it. Is there a way I could not use the x? Notice that cosine of theta, if we think about adjacent over hypotenuse, would be 45 over d. that would mean that D would equal 45 divided by cosine of theta. That's still not quite right, because theta, that's not t. We know the change in theta over the change in time is 1.6 minutes. If we just assume theta initial is 0, I wonder if we can do this so that we can say that this means theta will change 1.6 degrees for every minute that has passed, so 1.6 t, and that's in degrees. We might want to convert that to radians, in which case it would be 1.6 times pi over 180 times t. So we could rewrite this as 45 over cosine of, I should have already went to sleep, 1.6 times pi over 180 t. I'm going to check the answer key. Okay, that's what they have. Let me start this problem to make sure that we work on it in class. To find a function that relates the plane's distance from the Air Force Base measured in Air Force Base C measured in miles. So now they're calling this x that I've made C as a function of the elapsed time t since leaving the base. Okay, so I think that we could use trig again. We could say, so notice from the picture of the opposite over the adjacent, tangent of theta equals c over 45. That means c equals 45 tangent theta, and since we want this as a function of time, we'll just replace that theta with 1.6 pi over 180 times t, but I can't forget the tangent. Use your function c to complete the following table. Okay, 45 tan 1.6 pi times 180 over t. So I just need to plug 0 in for t. And tangent of 0 is 0. So yeah, I'm going to go ahead and do this. Since I've converted this to radians, then you have to make sure your calculator's in radians. If you didn't, if you just use 1.6t, then your calculator can be in degrees and it'll still work. So I'm going to go ahead and fill this table in. Okay. Now I think I need to work on the rest tomorrow, so I'm going to go to sleep and pick this back up tomorrow. Okay, now we need to find delta C over delta T, the average rate of change. So for this first one, we're just going to take 6.284 minus 0 over 0.5 minus 0. So that's the change in distance over the change in time. And we get 1.2568. I'm going to go ahead and fill out the rest of these. Describe how the plane's distance from the Air Force Base C, measured in miles, changes as a function of the elapsed time during the first 2 minutes. So we have our first 2 minutes here, and notice the plane's distance is increasing. Now these average rates of change seem pretty close together. They're increasing slightly. So there's not a constant rate, but the plane's distance is increasing at a slightly increasing rate. Okay, so again, just plugging these values into the tangent function, computing the average rate of change, I'm going to go ahead and fill out this table. So notice that the plane's distance is increasing, but now you can see that the rate is increasing pretty dramatically. Describe how the plane's distance from the Air Force Base C changes as a function of the elapsed time between 42 and 56 minutes since leaving the base. So it appears the distance increases at a dramatically increasing rate. Are these values realistic or are not? I'm not sure if this one is. This means that the plane is traveling at 1,719 miles per minute. I'm not sure if planes can travel that fast. These seem more realistic, 60 miles per minute, 21 miles per minute, 11 miles per minute, but I'm not sure about that one. So why is it not realistic? Let's see. I'm not sure. Maybe we can look at part G. That'll give us some insight. Graph the relationship between the plane's distance from the Air Force Base and the amount of time since leaving the base. What does the graph and the tables in part D and E convey about the speed of the plane? So I went ahead and set up my graph. This is time, and the vertical axis represents distance. We can look at our table values and see early on when the number of minutes is very small, there's very small changes in distance. It's increasing slightly, but not very much. Something like this. This is 10. So, yeah, then when we get to 42, we're already at 107.058. So we're up here, but notice that there had to be a very gradual increase to get up to that point. Then, let's see, 45.5, we're at 145, so we start jumping, let's see, getting steeper kind of quickly. Let's see, so at 49 we're at 220. At 52.5 we're at 428. And at 56 we're at 6,000, so we have a huge jump. It's pretty much some sort of vertical asymptote, it appears. So you might want to think about what's the time value that makes this denominator 0? I'm curious now. So if we take cosine of 1.6 times pi over 180 times t, set that equal to 0. Well, cosine would be 0 if this equaled pi over 2 or 90 degrees. So if pi over 2 equaled 1.6 pi over 180 times t. Our pi's can cancel out. This means 90 equals 1.6 t. And what's 90 divided by 1.6? $56.25. There's our vertical asymptote. Now, I'm curious how that relates back to theta. What would theta be? Theta would be 1.6 times 56.25, which would be 90 degrees. So, as this distance increases, notice the angle theta keeps getting larger and larger, approaching 90 degrees. And as we approach 90 degrees, the cosine will approach 0. And that means that we'll be dividing by 0, or we'll have infinity. We're going to have a vertical asymptote at that point. Probably what would really happen with this plane is the plane would start out and it would kind of travel at this same sort of trajectory, gradually speeding up, but then it would probably just reach a point where it would stay at a constant rate, like a cruising altitude. So it's probably not accurate for some intervals of time to say that this function that we created really relates the distance between those, because we said that the angle theta is changing at 1.6 degrees per minute, but that's just initially how it's changing. So when we get pretty far away from the airport, then that's probably not going to hold.